Okay, let's get started. Because I know that you're all perfectly rational, and because someone explained to me that the benefit to not being here today is that you get to buy a cheaper ticket to get wherever you're going, we now know that everybody who either lives a long way from here or rationally predicts that they're not going to get much value out of this class is not with us. We don't. That's under the assumption of rationality, of course. Okay, so what are we going to do today? I'm going to quickly review Bayes' rule, go back to the rainy day, cold day, use the square. I want to make sure that the math makes perfect sense and that you know how to do it. And then we're going to go through. I've sort of showed you. So Bayes' rule is this thing that I can make a pretty strong claim is the right way to do probability inference. The only sort of rational way to get it right. And I've shown you one anomaly, which is you guys getting the probability of an HIV positive test being sort of a true positive, getting that wrong, and everybody else gets it wrong too. I'm going to show you another anomaly in the context of a very important public policy, stop and frisk, which is sort of all part and parcel of the set of issues that are currently setting Ferguson, Missouri, and other parts of our society on fire, having to do with sort of race and policing. And then we're going to introduce our first sort of alternative behavioral approach to maybe some kind of irrational probability inference and start looking at whether or not that model can explain discrimination in stop and frisk policies. Okay, quick announcement, problem sake has been posted. It's due Thursday. You should be able to get started on it. You should be able to do almost all of it after today's lecture. Okay, so let me just quickly review what we were, sort of how I want you to think about Bayes' rule. So let's go back to the rainy days, cold days situation. Suppose we know the base rate probability of any given day being rainy, the probability of rain, or not rainy, the probability of no rain, which of course in a simple two state of the world case is just 1 minus the probability of rain. In addition to that, what we need to know to implement Bayes' rule is the probability of any given rainy day being cold. That's the probability of cold given that we see rainy. As much as I really stand behind the activity you're engaged in, I would like to ask you to hold that for later. So this is the probability that it's cold, conditional that we already know it's rainy. And also of a dry day being cold, right? So these are conditional probabilities that we already observe, and we're going to use this set of probabilities to infer the conditional probability we don't observe, which is the probability of a cold day being rainy. So someone's told us that it's cold, we haven't been outside, so we don't know if it's rainy. Okay, cold is the signal I, rainy is the hypothesis H. So given the signal that we know it's cold, what's the probability that the hypothesis we're interested in, rainy, is actually true? All right. So this is review, but I think it's because it's a bit simpler than the whole high, low, medium, value, or quality mutual fund manager. I think it'll be a little bit easier to get what's going on. So you have this square. This square is 1 unit high and 1 unit wide, okay? So it represents a probability of being rainy on this axis and probability of being cold on this axis, okay? So without putting in any numbers, let me say that, I guess this is probably Portland, and this distance here, right, a number between 0 and 1, is going to be the probability of rain. Another way of saying that in a frequentist approach is that that's the proportion of days that are rainy on average. And then this would be the probability of it being not rainy. These are base rates, okay? So the hypothesis that we're trying to test is whether or not it's likely to be rainy. So we have base rates. Then what we want is we want to sort of say what's the probability that we would see the signal, right? This is like what's the probability if a person was HIV positive that we would get an HIV test. What's the probability on a day that is known to be rainy that it would also be cold, okay? So this is the conditional probability that it's cold given that, right, what's the sort of the proportion of rainy days that are cold. So this is cold and rainy. That's a not very good ampersand, which is sort of this event that you see the signal in a situation where the hypothesis is true. And then we have some idea that on not rainy days it's also sometimes cold, perhaps not as often, so we model the probability that it's cold on a non-rainy day. Fine. This is all the machinery we need for Bayes' rule. Okay, so I is that it's cold and H is that it's rainy. The probability that it's rainy, given that someone has already told us that it's cold, is the probability. Can you guys all see this in the back? Sort of? Yeah, okay. So if the probability that it's rainy and cold, it's the probability that it's rainy and we see, the probability that it's rainy and cold, which is this, right? That's the proportion of all days when it is rainy and cold, divided by the probability that it's cold, okay? Which is this area plus this area. So this is cold and not rainy. So I'm going to call this area A and this area B. Right? So this is equal to A over A plus B. And another way of putting that is that we're going to take the area of this, not as a proportion of all days, but just as a proportion of cold days. So it's cold, rainy days as a proportion of all cold days. So we're normalizing this probability by the probability that it's cold overall, rainy or otherwise. Sorry, that it's rainy, cold or otherwise. That it's cold, rainy or otherwise. All right? So that's the basics conceptually. Then the math that you're actually going to compute this, and the place where we're actually going to start to get into an alternative model of base rate neglect, is to figure out what that area is. Well, it's the probability that it's rainy, right, this, times the probability that it's cold if we already know that it's rainy, right? That's the area of A. So it's the probability that it's rainy times the probability that it's cold, given that we know it's rainy, divided by the area of each of these things added together. So always this again, probability of rainy times the probability that it's cold, given that it's rainy, plus the probability that it's not rainy times the probability that it's cold on a not rainy day. That's the operational math that you need to have emblazoned on the inside of your forehead so that every time you blink your eyes you see it. Okay? Now, I think that this page of notes will now serve you as a thorough sort of cheat sheet kind of guide to everything you need to know about the correct Bayes rule. Now, yeah.
Do we have to get the correct answer or know the answer?
Both. I mean, in a problem, which we'll do in a second, you would just have all these numbers. And you just crank the handle. Okay. Now, let's start thinking about a real-world example that we could try to apply this to. So I wrote this lecture last year And it's funny because last year when I wrote this lecture, it was smack in the middle of a whole big controversy about New York City's stop and frisk policy. And I guess if I'd rewritten it this year, it would have been not about stop and frisk, but about when a cop should draw their gun, right? So you sort of draw your gun if you think the person that you're trying to apprehend might kill you, which has a lot to do with whether or not they have a weapon. So rather, which is, well, actually is going to turn out to be exactly the same inferential challenge as in stop and frisk, except that stop and frisk is in a sort of less of an emergency situation. Okay, so here's the policy goal. Get guns, drugs, criminals off the street of New York City, or any city for that matter, but this is all focused on New York City. We'll focus on guns for simplicity. So here's the New York City Police Department policy. Stop people when they look like they might have a gun, which is to say if you think you have a reasonable suspicion that they might have a gun, and then frisk them to find out if they actually do have a gun. Is this thing? Nope. So I have to do, that should solve the problem. Yep, okay. So stop them if you have reasonable suspicion to think they might have a gun, and then frisk them, right, which is what they do at the airport. They pat you down, except at the airport they do it like this, and if you're on the streets of New York City, like this. Just to make sure you know who's boss. Okay, here's U.S. law, which of course the New York law has to abide by. A stop is justified if a person exhibits any combination of the following. So some of these are just fabulous. If you were writing like a fictional account of a country on a foreign planet, you'd come up with cool stuff like this. Appears not to fit the time or place. Sir, in my judgment, you do not fit the time or place. It's like, all right, let's plan this for another time or place. Okay, matches the description on a wanted fire. Seems reasonable. Acts strangely or is emotional, angry, fearful, or intoxicated. Well, I'm never intoxicated, but I'm emotional, angry, and fearful a lot of the time. Anyway, you can see that the point of this is not to say that it's silly. It's to say that there's an enormous scope for judgment, right? Judgment is a huge chunk of what we call judgment is making judgment calls about how likely things are. I made a judgment. I thought that blip on the radar screen was likely to be an enemy ship. Turned out it was an iceberg. Well, so I made the wrong judgment. Okay? Loitering or looking for something. Be sure you don't look for something around a cop. Okay, fine. So I guess if you look for something and find it, then you're on solid ground. A frisk, so if you feel that a stop is justified, then a frisk is justified under certain situation. You know, there has to be a heightened reason for you to think that this is a good idea to actually stop someone and actually physically frisk them, right? So concern for the safety of the officer, suspicion that the suspect is armed and dangerous, time of day, behavior, emotional state, the look of the suspect, okay? A lot of this, so anyway, the point is that this policy, you can write down whatever words you want, but at the end of the day, this kind of policy, and true in lots and lots of settings, hinges crucially upon the functioning of the human brain, okay? All right, so let's look at some numbers. This is New York City. Okay, so this is the controversy. African Americans and Latinos, who I'm going to refer to for the sake of simplicity as people of color. I know that there are a lot of other categories of people who are thought of or think of themselves as people of color, but just so that you all think that I actually am an economist. You know, economists like to just make broad, often very offensive simplifications. So this is my simplification. I'm going to call people of color, African Americans and Latinos, are stopped and frisked far more often than whites and Asians. Okay, so here's the actual police stops. Okay? This is African Americans. 53% of stops are African Americans. Another third are Latinos, and a mere 13.3% are white and Asian. Now, even more offensively, I'm going to spend the rest of the period talking about people of color, Africans and Latinos, versus whites. Okay, so I'm leaving out tons of people, and I'm getting the categories wrong, but the essence of the policy issue is, I think, appropriately represented that way. Here's the actual breakdown of the population. 23% African American, 47% white and Asian, 29% Latino. You see the problem, right? Sorry. You see the issue. We don't actually know yet if this is a problem. We know that it's an issue. It bothers a lot of people a lot. And it looks like the police are being biased. Okay? So they're stopped and frisked disproportionately to the population of the city. Clear? Policy situation's clear? Do we have an anomaly? What would make this not an anomaly? Yeah, Nick. Right, so what if it turns out that when they stop African Americans and Latinos, they're actually much more likely to come up with a gun? Then in some sense you might say, well, then that's justified. They're looking in the right place. Perhaps. Yes? Did anyone have another thought? Okay. There are other possibilities, but that's sort of the main one that people think of. Okay. Now, okay, so fine. Clicker question. When would it be good policy to stop and frisk people of color, POCs, disproportionately? Under what sort of conditions of probabilities of one thing compared to probabilities of another thing? All right, so why don't you give it another 3, 2, 1. Everybody in? Okay. All right, so let's just see what you're saying. So it looks like modal answer B. Plenty of people think that it's A or C. Where did that go? So most people think that the probability of a gun, if we know that you're a person of color, the probability you have a gun conditional on a person of color has to be bigger than the probability you have a gun conditional on being white. Let's just, before actually investigating the truth, let's just walk through a simple model of what economists refer to as statistical discrimination. Okay? Statistical discrimination means when you discriminate, that is to say, behave in a way that is biased towards or against one group or another, but for statistically sort of valid reasons, based on what you know about sort of the statistics of one group versus another, which usually means probabilities. Okay? So economists have shown, I should put quotes around shown, that racially disproportionate stop and frisk can be rational, where have shown means that they've written down a model, right? And where rational sort of means that it's the utility maximizing or sort of net benefit maximizing thing to do. Okay, so here's how models like that go. Now this is an extremely stripped down model that would never. It's so simplified that it's simplified enough to get the intuition, which is the right amount of simplification. So consider a police officer deciding who to stop and frisk. Okay, here are the parameters of the model. We have a value of finding an illegal gun. We're just going to assume that that's constant regardless of your race, color, or creed. Okay, V of G. Come on now, where did you go? We have the cost of a stop, C, which is the time it takes for the cop, the cop's time and the things that they could be doing with their time. The probability of a person of color or a white person, just designated by W, carrying an illegal gun. So the probability of a gun, given that you're a person of color, and the probability of a gun, given that you're white, right? So I stop a person of color. I have in my mind some idea of how likely it is that they're carrying a gun. And now, mind you, they're observing lots of other things, right? Are you looking for something? Are you being furtive? Are you in the right place at the right time, etc.? But I'm just going to focus on the signal race, okay? Holding everything else constant. Okay, and the final thing, and this is actually the police department or the police officer's choice variable. This is a policy variable, okay, is the proportion of stops that are of people of color. So RPOC, which is between 0 and 1. That's not a random variable. That's something that the specific officer or the department as a whole chooses. Go out and make a third of your stops be people of color, or go out right like that. And a lot of that has to do with where in town they send their patrol cars, et cetera, okay? So this, like I said, so this is a choice variable or a policy decision. So what we want to know is what's the average net value of all stops, or the average value of a stop, where that average is over stops of people of color plus stops of whites, which is chosen by the cop, and averaged over the probability that you'll find a gun on either category of person which is not chosen. Okay, so the weighted average is the expected value of stopping a person of color and the expected value of stopping a white person, given the probabilities that a POC or white person will be carrying a gun, of course, minus the cost. All right, so I'm going to do some math in a couple of steps. How do we determine, when we write down models, what is the mechanism we use to come up with a prediction of what a rational utility maximizer or even an irrational utility maximizer will do? Okay, on the list of things that you should be able to, on the list of questions that you should be able to answer immediately after you graduated with a major in economics from UC Berkeley, this is priority number 1. What is the assumption we make about how people make their choices? No, we don't always. You said the wrong thing first, and then the second thing you said was right. But you said something else, and Nick is going to repeat it. Maximize utility. Okay, we should probably all just chant it for a little while. Okay, everything that we do is based on maximizing something, either a profit function or a utility function or a social net benefit function, something. Okay, so to get there, we need to write down an objective function, right? In this case, I'm going to call it an expected utility function, but you could think of it as net benefit to society. You could think of it as the utility of the cop or of the police department. It could be in any units, but we need to have an actual. We need to take this model set up and turn it into a utility function. That is always the first step in doing economic modeling. Okay, so what we want is this. This is an expected utility objective function because we don't know whether or not we're going to find a gun on any given stop. Okay, so the expected utility as a function of. So we're choosing something by maximizing utility, so the utility function better be a function of the thing we're choosing, right? So this is a function of, sorry, the proportions? Or what proportion in this case? The way I've set it up is the policy choice is what proportion. Okay, so it's the expected utility as a function of RPOC, from which we get RW for free because it's 1 minus RPOC. Okay, so what is it? There's going to be some cost we're going to deal with at the end, but what we want is a weighted average of the expected value of stopping and frisking a person of color and the expected value of stopping and frisking a white person. Okay, so it's weighted by RPOC. So if you're going to go half and half exactly, then it's sort of a 50% mix of the value of pulling over a person of color and the value of pulling over a white person. So the expected utility of pulling over a white person, right, is the probability. A person of color is the probability that of finding a gun conditional on stopping and frisking a person of color, right, times the value of a gun. Okay. So this is how often you pull over people of color, this is how often they have guns, and this is the value of a gun. Okay? Right? Plus 1 minus RPOC, this is the proportion of pullovers that you choose to make white people, times the probability of finding a gun on a white person times the value of a gun. Now, of course, you could factor out VG if you wanted, and then minus C, right? Because each one of these has got the same cost. This, by the way, is where our model is most oversimplified, is that, in fact, this cost probably is more complicated than just the same for everybody. If that's the expected utility function, okay, under what conditions should you make RPOC high or low? Under what conditions would you want to just really focus your attention on pulling over people of color? Sorry? Right. So if this thing is high, then you would want to high, and you can say something much more specific than just high, if it's higher than that, right? Now, the sort of fourth thing on the list of things you need to be able to say to people after you graduate from here with a degree in economics is somebody says, okay, well, what's the first order condition for maximizing the utility function? Of course, everybody, if you're talking to a taxi driver there, that's always going to be the second question they ask you. Right? If this, what do we do to figure out what value of RPOC maximizes this? Take a derivative. Let's take the first derivative. So this thing is either getting smaller or larger as RPOC changes, and maybe it's getting larger first and then smaller, maybe it's getting smaller first and then larger, and we're going to find out something about its slope, and that'll tell us what we should do to RPOC in order to make this thing big or biggest, big, bigger, or biggest. Okay? So the derivative of this expected utility function with respect to RPOC is actually quite simple. This is just a linear combination. So it's the probability, it's a conditional probability of finding a gun on a person of color times the value of picking up a gun minus the probability of picking up a gun on a white person times the probability of picking up a gun. The cost obviously doesn't fit into it. What do you notice about this? Right? So this is a situation. So the first thing you should notice is that it just doesn't include RPOC. So we cannot now actually find a maximum, because you would find a maximum by setting this equal to 0. That's the place where the slope is 0. You're at the top. You can't do that because there's no RPOC. That should immediately tell you that you're looking at a corner solution. That should immediately tell you that this is a situation where the choice variable is going to be at one end or the other of the possible range. So in this simplistic model, you're either going to pick up all people of color or all white people. Okay? Because of how simplistic I made the model. The question is this increasing or decreasing in RPOC? If this is the slope of the expected utility function, if it's positive, right, which is to say the more you increase the proportion of people of color that you pull over, then you should just go all the way. If it's negative, which means that the more people of color you pick up, the lower the expected utility goes, then you should go all the way down. When is it positive? Do you need it? This thing's positive when this is bigger than that. And since these things are the same,